Okay, we're going to take a look at synthetic division. Not that long ago, we took a look at polynomial division, and I mentioned there would be something similar that we could only use with linear divisors going forward. Here's long division if you'd like to remember how that looks. Take a look and compare them with synthetic division. Some key differences are just using the coefficients. You'll notice that the divisor is written with the opposite sign because it's actually the root that they're writing here. We will be bringing things down, multiplying, but then adding. The answer is going to be year. That's obviously just kind of an organizational thing. But in general, compare and contrast, and you'll see rather similar patterns emerging. So here's a pretty simple problem to show the basics of synthetic division. I am going to write just the coefficients of each of these in order. If something is missing, then I need a placeholder with 0. So 1, 8, 31, 54, negative 24. There were no terms missing. And I'm going to divide that by x plus 4, which means the root is negative 4. We still bring down. If there's a remainder, it will go in this box here. Then we multiply and add. Multiply and add. Multiply. Always multiplying this and adding together. And then we multiply. I need to make sure I have the right signs. Sorry, 15, yep. And add, this is still going to be negative, positive 24. And add those together, we'll get 0. So if I were to divide this polynomial by this linear polynomial here, you would get x cubed. We're always going down 1 because x to the 4th divided by an x is going to give something with an x cubed, which you could also do constant linear squared cubed. So 1x cubed plus 4x squared, 15x minus 6 with no remainder. Here's an example one with a remainder. Same idea. I do see that I have an x to the 4th and x terms that aren't marked on here, and I will need a placeholder with a 0. So 1x to the 5th, no x to the 4th, negative 8x cubed, 2x squared, no x's, and 1. Okay, and the 3. This will be my remainder box. 1, 3. Adding, you'll see this goes much more quickly than long division. 15. And then as you put in this, we'll get the remainder of 46. So if we were to write out the quotient of this with the remainder, you'd get that it's x to the 5th divided by x is going to give me something with x to the 4th. You can also count those and figure out what's left. 3x cubed plus 1x squared, 5x plus 15. And then there's this remainder of the divisor, not quite a full one left over. So that will be the solution there. Here's a theorem that you can use to connect
the little things in life. Thank you.
This nice remainder here. You can use this because it's so quick to be able to calculate a lot or tell you more about the polynomial, and we will use that going forward. If you were to divide that, remember that we found it had a remainder of 46. What this would mean is if you put 3 into that function, you would get this value out. So the remainder is equal to the function at that value of x. Here's an example here. What is the value of f of 4? You could put f of 4 in. It's not entirely a fun calculation to do. Perhaps this is easier. There is no x. 12, 48, 4 times 51. It doesn't necessarily mean it's going to be easier here, but not all that bad. 198. 200 times this would be 800. Take away 4 was 792. And 4 times that. So there certainly is a little bit to do here. 800 times 32 minus 8 times 4. 800 times 4 is 3,200, so 3,100, and take away 32. 68, so 3,169 should be, so f of 4. Okay, still not a nice number, but it is significantly easier than doing that. More importantly, though, is what this will tell us about the roots. So if it's a factor, okay, then this is only true if and only if you have that when you put that in, you get 0 out, which makes sense. That's the whole idea of a root in. But imagine you have this polynomial, this quartic on top, divided by x plus 4. You get no remainder. That means it's a factor, right? Because there is no remainder. It goes in perfectly. You'll also notice if you put in -4, you get that it equals 0. Again, that makes sense if you think of all these quadratics and you say, okay, well, if that can be factored to x minus 4 times x minus 3, of course, putting 4 in is going to give you 0. So it's really just a higher application of this and the remainder theorem. So 1 or 2 more things here. Show that these two terms are factors of this polynomial, and then we're going to fully factorize it. So up until now, we've only looked at factoring quadratics. 2x cubed, oops, I only want to write the coefficients. And 15, it doesn't matter which we start with. I'll do the 3 first. Bring down, and then just keep going through. So 15, oops, I got some, that's going to be negative 15, 0. So we showed that this, since the remainder is 0, that means it's a factor. And we can keep going on that, okay? Fully factorize it, but now I want to put in what happens if I put this factor in. That's no longer involved. We can do that here. 2 times -1, -2. Sometimes I get going too fast. Oh, same thing there. Okay, so it's also a factor. If it's a factor of the quotient, then it's also a factor of the original polynomial. We will also get here that this is the final one. So this is 2x plus minus 5. Write that right here. That's what's left. So x minus 3 times x plus 1, 2x minus 5 is going to be the factored form of this polynomial. Okay. Oops, we have